Hello, my name is Nick Murthy. I am an engineering ambassador studying computer and systems engineering and computer science at RPI. I will be guiding you through this 7-session current solar panel program. Before we begin, make sure you have completed all the steps in the initial setup handout on our website. This will make sure you are prepared to follow along during these sessions. In this program, I will be teaching you about circuits, solar panels, C++ code, and Bluetooth signals. Learning these skills and concepts will enable you to understand the device you will be building. You will be learning through activities, demonstrations, and presentations. The end goal is to create a working solar panel device that can wirelessly send data to your computer. Here are the two solar panel devices that were created by both undergraduate and graduate research students here at RPI. The second version on the right is the one you will be learning about and constructing yourself. This is the wiring diagram for the new solar panel module you will be constructing. It might look a little complicated now, but we will be going through each component step by step so you get a full understanding of how the system works. To aid you in following along with this program, wiring diagrams such as this one and other helpful handouts can be found on the website. I will make reference to these on occasion, but they are mostly there to help you follow along and learn the material. For some background information, this device was first created to collect solar radiation data to simulate solar panels on the military grid. From the collected results, soldiers could fairly accurately analyze how much power massive solar panels would generate in certain areas on the grid. As you can see on the right, their microgrid would consist of solar panels, wind turbines, and other sources of power. They would use this power to run all of their operations. This program consists of 7 sessions, during each of which you will learn new concepts and skills in order to help you build and understand your solar panel device. In the first session, you will learn about circuits. In the second session, you will learn about the Arduino, the current sensor, and the IDE. In the third, you will learn about solar panels and you will start your main experiment. In the fourth, you will learn about C++ code and you will test your device. In the fifth session, you will learn about signals and Bluetooth, and in the sixth, you will complete your experiment and there will be a small quiz on what you learned. The seventh session contains a couple of optional final activities for you to complete if you would like to test your knowledge. To begin, I will teach you a bit about circuits. In order to understand circuits, we first have to know what a battery is, since we will be using batteries a lot. A battery is a container in which chemical energy is converted into electricity and used as a source of power. It consists of a cathode, an anode, and an electrolyte. A cathode is a positively charged electrode, and an anode is a negatively charged electrode. You can think of them as conductors with a specific charge, where a conductor is a substance that can easily transport charges or electricity. The anode is negatively charged because it releases electrons. It also releases ions in the electrolyte in order to form a current between itself and the cathode. The cathode, on the other hand, is mostly absent of electrons. Due to this, electrons will flow in the external circuit from the anode to the cathode. This creates a current that can power devices such as the light bulb in the image. An important note to make is that even though the electrons are moving from the anode to the cathode, current is said to go the opposite direction, because we define the direction of current as the flow of positive charges. Now we can quickly talk about Ohm's law. The law tells us that voltage is equal to the current multiplied by the resistance. Voltage is the potential difference between 2 points in a circuit. You can think of this as the pressure in a water pipe. The current is the measurement of the flow of electrons. Think of this as the flow of water in a pipe. Lastly, the resistance is the measurement of how much current flow is restricted, which is similar to how wide a water pipe is. The last important measurement we will be talking about is electrical power, which is the rate at which electrical energy is transported through a certain point in the circuit. We can use the equation power is equal to current multiplied by voltage to find the power in watts. The image on the right demonstrates how a light bulb needs a voltage and current in order to consume power and produce light. The battery is supplying the voltage, and because there is a complete circuit from the positive side of the battery to the negative side, a current is produced. This results in the bulb lighting up due to the resistance inside it, which is transforming that electrical energy into power in the form of light. However, if we have a voltage and a resistance, but we break the circuit by lifting the switch, we can cut off the current and turn the light off. Since power equals current times voltage, if the current is zero, there is no power produced or consumed. Now we can discuss the two types of circuits. There is a series circuit, in which all components are one after another. In this diagram, we show resistors, which are components that slow down the flow of current. You can think of resistors in a series circuit as one large resistor, since you can get the total resistance of a bunch of resistors by simply adding them all up. A parallel circuit has components that are not one after another and are instead found in multiple branches or pathways of the circuit. We can think of a series circuit as a line of customers in a grocery store with one checkout. The customers are electrons, and the checkout is the resistor. Because there is only one checkout, there is only one path that the customers can take, and so the customers move slowly. This is similar to how the electrons in a series circuit flow slowly because there is only one path for them to take. For a parallel circuit, you can think of the same analogy, but now there are multiple checkouts. This results in a higher flow of customers, since customers have multiple paths to take. Sometimes, there are different valued resistors in a parallel circuit. In that case, each resistor pulls its own amount of current. This is similar to how in a grocery store, there could be fast cashiers and slow cashiers. Let's real quick go over how to calculate current in a series circuit and in a parallel circuit. In a series circuit, the current is the same through all components. We can find this current by taking the voltage from the battery and dividing it by the total resistance in the circuit. This equation is the same as Ohm's law, but manipulated so we are solving for I, which is current. Now if we add the resistors together, we get the total resistance, which is 18 kiloohms. We can then plug in the 9 volts in the 18 kiloohms into our equation, and we will get 0.5 milliamps. Let's now switch over to a parallel circuit. Each resistor produces its own distinctively separate current. Even though there is a different current, they all share the same voltage, which is 9 volts in this case. So, in order to find each current, we simply use the equation as before, but we will do this for every resistor individually instead of adding them up. We plug in the 9 volts and each resistor's value, and we get 3 milliamps, 0.9 milliamps, and 1.8 milliamps. As you can see, the currents are bigger than that of the series circuit. Why is this? Well, the electrons are allowed to flow in different pathways, so the total flow of electrons, or current, is higher. These electrons aren't forced to pass through one large resistor as they would be in the series circuit. The last important component we will talk about here is the LED. LEDs, also known as light-emitting diodes, are similar to resistors in the sense they can convert electrical energy into another source of energy. However, instead of heat, they convert electrical energy into light. In addition, they have a much smaller resistance than resistors, which means you have to be very careful when attaching a battery to an LED directly. Doing so will allow a massive current to pass through the LED, which will burn it out. When electrons flow through an LED, the electrons release energy in the form of photons, or light. Also note that LEDs are a form of diode, meaning they only allow current to flow through them in one direction. Most LEDs have one longer pin and one shorter pin. The longer pin is the positive side, and the shorter pin is the negative side. Before we start the activities, we have to first discuss what a breadboard is. A breadboard is what engineers use to test their circuits before soldering components together. The positive and negative strips connect all the holes in their respective columns together. You will want to attach your positive pin and negative pin from the battery to the correct rails as indicated by the symbols on the breadboard. The holes in the center of the breadboard are for electrical components like LEDs and resistors. Instead of going vertically, the inside section has wires underneath that connect holes horizontally. When adding things like LEDs, you want to attach each pin of the LED on separate horizontal holes as shown above. If we put them on the same row, no current would flow through it, because electrons would rather flow through the underlying wire, which has less resistance. If we put the prongs on separate rows, the electrons are forced to flow through the LED and it will light up. Now you will start the first activity. The objective of this activity is to find out how many LEDs we can get to light up in series before they all won't light up anymore. Hello, I'm Nick. I'm going to be demonstrating activity 1.1. Now in this activity, we want to see how many LEDs we can connect in series before they turn off. Now for this activity, you're going to need a 9-volt battery, a 9-volt battery clip, a 470 ohm resistor, about 10 of these LEDs, and various jumper wires. Let's get started. Alright, so the first thing we're going to do is connect the 9-volt battery to the 9-volt battery clip. Now once we do this, we can connect the leads of the battery to the positive and negative ends of the breadboard. So we're going to connect the positive end of the battery to the positive end and the negative end to the negative side. Now we're going to connect our 470 ohm resistor in series with the positive end of the battery. Now from here, we want to connect a bunch of LEDs in series and see how many of them we can connect before they all turn off. So we're just going to start by adding one LED. And remember, when we add the LED to the circuit, we want the positive end to be the longer side of the two leads. So we'll connect this right in there. And then lastly, to complete the circuit, we need to connect the negative side of this LED to the negative side of the battery. And as we can see, the LED turns on. Now, we want to see if we can connect more of these LEDs in series. So let's try adding maybe two more. Now remember that in series means the positive end of one LED is connected to the negative end of another LED. And so we will continue adding them in this sort of line. And let's connect all of these together. As we can see, they still light up. So that means that we can add more in series. So right now we're at 3. Let's add another one here. Let's see if 4 will light up. As we can see, 4 lights up. We can go ahead and add a 5th one here. You can see all 5 of them light up, but it's a lot dimmer than when there was only one. So let's see if we can get a 6th. Now at this point, we can see that the LEDs don't turn on very much at all. So the maximum amount of LEDs we can get in series is 6. Now we will move on to the second activity. We want to try and figure out how many LEDs we can connect in parallel before they all turn off. Alright, so now I'm going to demonstrate activity 1.2. Now the purpose of this activity is to see how many LEDs we can connect in parallel before they all turn off. Now for this activity, you're going to need, again, a battery and a 9-volt battery clip, a 470 ohm resistor, a bunch of red LEDs, and a bunch of jumper wires. Let's get started. Okay, so again, the first thing we want to do is connect the 9-volt battery to the clip and connect the positive and negative ends of the battery to the positive and negative ends of the breadboard. And then all I have here is that 470 ohm resistor. Now, in order to connect all of these LEDs in parallel, we need all of the positive ends of the LEDs and all of the negative ends of the LEDs to be connected to each other. So we're going to start by just adding 2 LEDs in parallel so we can see how the circuit's going to look. So if we connect one LED to the positive side, or connect its positive side to the resistor, and then we'll take another LED and connect it right next to the other LED. Now, these 2 LEDs have their positive ends connected and their negative ends connected. And again, to complete the circuit, we want to connect the negative end of the LEDs to the negative end of our battery. Now it appears that our LEDs have not turned on, so we make sure that they're put in the right way. Looks like they are. It's possible we have a dead LED. Try a different one. There we go. So now we see that one of these is turned on, and perhaps we have 2 dead LEDs. And there we go. So now we can see that both LEDs have turned on. Now we want to continue adding more of these LEDs in parallel, and we're going to do that by, we're just going to bring the positive end of this circuit down to here, and we'll add more of these LEDs in parallel. So we can put one in here, maybe another one next to this one, and we'll see if we can get one more next to all of these. And again, all of these LEDs have their positive and negative ends connected to each other. So to complete this circuit, we want to connect the negative side of the first set of LEDs to the negative side of the second set of LEDs. And we want to connect all the negative ends together. And as we can see, it looks like 4 of these LEDs have turned on. One of them did not. Let's try and replace this with a different one. There we go. So now we have 5 LEDs in parallel, and those are all lit up. Let's see if we can add some more. So again, we will bring the positive side of everything down to here, and the negative side of all the LEDs down to here. And now we'll go ahead and add more of these LEDs in parallel. So here is a 6th and maybe a 7th, and we will complete the circuit. And as we can see, all 7 of them turn on. So already we have more than what we had when we connected them all in series. And in fact, we can continue adding LEDs up to about 10, and we will still get them to all light up. So why can we put more LEDs in parallel? This is because each LED in parallel is using the same voltage after the resistor. While in series, the voltage will drop progressively after each LED. Additionally, LEDs in parallel have a much lower resistance than those in series. This results in the current remaining relatively high when adding another LED in parallel. Our last activity for this session is a challenging one. Your goal is to create a circuit using 1 resistor, 1 push button, 4 LEDs, and as many wires as you need. This circuit should have 2 LEDs turn on when you connect the battery to the circuit. Then, when the push button is pressed, those 2 LEDs should turn off, and the other 2 LEDs should turn on. Think about how the resistance of a series circuit differs from the resistance of a parallel circuit. Okay, now I'm going to demonstrate activity 1.3. Now this activity is more of a challenge. We're going to try and see if we can build a circuit that has 2 LEDs that are on to begin with, and then we will press a button and we want those first LEDs to turn off and a second set of LEDs to turn on. Now for this activity, you're going to need, again, a 9-volt battery and a battery clip, a 470 ohm resistor, a bunch of LEDs, a bunch of various jumper wires, and you will need 1 push button. Let's get started. Okay, so in this activity, again, the first thing we want to do is connect our battery to our breadboard. And then we want to add this 470 ohm resistor in series with the battery. Now the first thing we're going to do is connect our LEDs in series with the resistor. And again, in series means the negative end of one LED is connected to the positive end of another. And now we're going to complete this circuit by connecting the negative end of these LEDs to the negative end of the battery. And as we see, these 2 LEDs turn on. Now we're going to use this push button to add a second path to our circuit. And so we're going to do that by connecting the push button here, such that its positive side is connected to the resistor, and its negative side isn't connected to anything right now. Just like that. Now we're going to connect the other side of this battery to a circuit down here. And in this circuit, we're going to have 2 LEDs that are in parallel with each other. So their negative ends and positive ends are connected together. And we're going to complete this circuit by connecting the negative end of the LEDs to the negative end of the battery. Now, if we press this push button, we see the original 2 LEDs turn off and the second set of LEDs turn on. Here is the solution wiring diagram for that activity. How does this circuit work? This works because a series circuit has a higher resistance than that of a parallel circuit. When the push button is pressed, it opens up another branch that the electrons can take. This new branch is the parallel circuit, so its resistance is smaller. The electrons then flow through the parallel LEDs because their resistance is smaller, thus turning off the series LEDs and turning on the parallel ones. This concludes the first session of the current solar panel program. I leave you with this quote: "What we usually consider as impossible are simply engineering problems. There's no law of physics preventing them."